Cross-encoders squeeze more relevance from each query document pair, while ColBERT reuses passage embeddings. We'll benchmark both and pick the best reranker for a fixed latency budget. You'll see how to connect the pieces into a workflow that compares rerankers, plots relevance against latency, and chooses within a budget. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Search in a RAG system pulls two opposite levers at once. Give the generator the best passages and keep latency low. Cross-encoders are precise because they score a whole query document pair with a transformer. But that precision costs time. ColBERT, by contrast, stores token vectors per passage and reuses them. So at serving time, it can score many passages much faster. Here's the concrete trade-off we'll study. With a fixed latency budget for re-ranking, do you pick a heavy per-pair scorer and re-rank fewer candidates? Or a faster late interaction scorer and re-rank more? The goal is to maximize the quality of what the generator sees, while meeting whatever millisecond constraint your app requires. The core idea is simple. First stage retrieval gives a candidate list. Then, a re-ranker reorders those candidates. Measure quality with nDCG, so ordering and graded relevance matter. Measure time with a P95-like estimate, so slow tails show up. Vary the candidate depth and plot quality versus latency to reveal a frontier. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we create the smallest re-ranking slice that still shows the trade-offs. This snippet creates the smallest re-ranking slice needed for a latency budget experiment. Candidate depth is already visible here. Candidate starts with one noisy hit, but the top depth still keeps two judged relevant documents. Quails uses graded labels, so later nDCG at 10 can reward putting D1 ahead of D3 instead of treating both as equal. Increasing depth gives the re-ranker more chances to recover relevant context, but it also gives slower re-rankers more pairs or token interactions to score. The visible output shows how much useful judged material survives the first stage cutoff. We need to see how ColBERT actually scores at token granularity. So next, we compute the MaxSim primitive. This example scores token-level query and document vectors with PyTorch to show the ColBERT MaxSim primitive. A late interaction re-ranker does not collapse each document into one vector before scoring. QVec is matched against every token vector in each entry of DVEX. The expression QVec at VT builds the token similarity matrix. Max1 keeps the best document token for each query token, and sum turns those best matches into one document score. The tiny tensors stand in for real ColBERT token embeddings, so the scoring rule stays easy to inspect. The output shows which document wins under MaxSim before any cross-encoder is involved. That gives us a fast baseline ranking. Now we want the cross-encoder comparison and to measure its real serving cost. This code runs a real SentenceTransformers CrossEncoder over the current candidate slice. The latency concern changes shape here because ce.predict receives explicit query document pairs. So a deeper candidate set means more transformer forward work at serving time. Timed MS keeps the model loading cost out of the measured call and wraps only the scoring path. Pairs is built from candidate/3. CE scores returns one relevant score per pair, and CE ranked sorts those scores back into document order. The visible output shows the top re-ranked document, confirming the cross-encoder path is producing a usable ranking. Quality numbers for a top 1 winner are useful, but RAG usually needs several chunks in order. So we convert ranked lists into nDCG. This snippet turns re-ranking quality into the metric we can plot against latency. Raw top 1 output is not enough for RAG evaluation because the generator usually sees several chunks, and their order affects what context is easiest to use. DCG discounts lower positions. Ideal defines the best possible ordering from queries, and nDCG normalizes each re-ranked list onto the same scale. Order is a small helper for later benchmark rows, where each model produces scores at each depth. The visible output shows the nDCG at 10 difference between CE rank and ColBERT rank, which is the relevant side of the budget decision. With scoring and a metric in place, we can sweep candidate depth and record time to build a latency quality frontier. This example builds the tiny latency quality frontier that guides the re-ranker choice. The SentenceTransformers CrossEncoder path still uses CE predict, while the ColBERT path reuses the MaxSim scores from ColBERT scores, making the serving time contrast visible as K grows. For each model and candidate depth, timed MS records 5 re-ranking calls. Sorted times -1 is a conservative nearest rank P95 estimate for that small sample, and nDCG order S supplies the quality coordinate. In a real benchmark, increase repetitions and use production hardware before setting a cutoff. The output confirms that 6 plotted points were produced. 2 re-rankers across 3 candidate depths. Mapped to a real system. Keep the same collection and crels. Run retrieval with your production index and measure this frontier on your inference hardware. The shape of the frontier tells you which model plus depth combinations stay inside the latency budget while giving the best nDCG. This is a concrete way to pick between a Cross-Encoder and ColBERT when latency matters. Use it when re-ranker cost affects user experience, and you can measure both time and graded relevance. One caveat: the frontier depends heavily on hardware and repetitions, so small test rigs can mislead. A clear next step is to tune the candidate depth K while running this benchmark on your production GPU or CPU, and use a larger repetitions count to stabilize the P95 estimate before picking a cutoff. If practical AI engineering helps you, subscribe and watch the AI engineering videos.